Good morning, good afternoon, good evening. Today's a great day to chat about skeletal muscle. I'm Dr. Luden, but for those of you who don't know me, my strong preference is to be referred to by my first name, which is Nick. So as the title slide indicates, today's topic is going to be the length-tension relationship. Now, this is a commonly acknowledged factor in the world of skeletal muscle. I know that you've all been exposed to this concept, but I will say, when we first teach this concept, usually it's in reference, neatly, to an individual muscle fiber or maybe an isolated animal muscle prep. Of course, what we're more concerned with is an anatomically intact human, and so we're almost always dealing with multiple muscle tendon units that are working across the joint. And so while the length-tension relationship is accurate, really what we're more concerned with is the joint angle torque relationship. And I think that hopefully I will bear this out over the next few slides. So let's get into it. Here are the objectives for today's chat. I want you to be familiar with the following concepts. You can read them for yourself, but I'm going to briefly review these. So first, I want you to understand that the length-tension relationship is just one of many factors that impact force capacity or force potential. I'll detail that on the next slide. I want you to understand what the length-tension relationship actually looks like in a muscle tendon unit. You should be able to differentiate between active force production and passive force production within a given muscle, while also acknowledging that there are multiple MTUs that are working across a joint. And so when we're looking at torque that's produced around a joint or an axis, it is the collective contributions from all of those MTUs that are working. I also want you to understand the impact that sarcomere spacing has in active muscle force production. Understand that that's muscle specific depending on the MTU of interest. I want you to understand it in very simple terms, the effects of a moment arm on force production or torque production, and understand that these are also muscle specific, in that both sarcomere spacing and therefore active force production, passive force production, moment arms, all of these things change within a given MTU and across MTUs differently as you change joint angle. So again, this will become more clear as we move through this content. So starting off, what we're going to talk about is all of, or many of the factors that impact your ability to generate force or torque around a joint. And there are many factors, including anatomical and physiological factors, that impact force production. And as you know, force production matters. It's not the only thing that matters, but it has a large impact on whole body function, whether it's you want to be able to power up the stairs when you're older, complete other activities of daily living, or you're trying to optimize athletic performance, or anything in between. There are lots of factors that impact this, including whole muscle size. So how much muscle mass do you have contributing to that force production? Of that muscle mass that you have, how much of it are you actually activating? Right, so this is a neural factor. How many motor units are you lighting up? What is the frequency of those action potentials? So this is another neural factor. Are you sending rapid action potentials, rapid signals to a given motor unit? Or are you sending slow action potentials to a given motor unit? Also, what's happening on the other side of the joint matters. So the magnitude of antagonist muscle force production will impact the net force production or torque production across the joint. We also know that fiber type distribution plays a role, particularly in dynamic force. Isometric force production, not so much, but that is beyond the scope of this session. Also, those of you who've had KIN 302 exercise physiology will understand that it's not just as simple as some of our fibers, our muscle fibers, are slow twitch and others are fast twitch, that it's a vast continuum ranging from pure slow twitch fibers to extremely fast pure 2X fibers, albeit those are pretty rare. Muscle architecture also has a large impact on force production. And this goes beyond just classifying a muscle as having multiple heads, being pennate, unipennate, bipennate, etc. What we're talking about here also includes pennation angle, fascicle length, and those sorts of features. Of course, exercise metabolism or metabolism in general matters. Energy availability and therefore the ability to recycle ATP to support the muscle contraction. There are anatomical factors as well. Of course, we're working within the constraints of our anatomy. One such factor is the length of a motor arm, which we'll get into actually later on in this presentation. And that dictates the leverage that a given MTU has around a joint. Of course, the force-velocity relationship also impacts force production, right? It's in the name. So as you are altering the velocity of a contraction, that influences how much force you're able to generate. And then finally, the length-tension relationship. And so that's going to be the focus of this session. But again, I want you to understand that this is one factor. It's an important factor, but it's one of many that contribute to our ability to produce force or torque around a joint. So here's our first look at what the actual length-tension relationship looks like. And as I will highlight a little bit later, because we're looking at a very popular joint, the knee joint here, it's not just a single MTU that is contributing to this curve that we see here, but rather the collection of multiple muscles. Also, calling it the length-tension relationship I don't think is fair. I just want to reiterate, we're talking about force production across the knee joint, and so we're talking about joint angle and torque production. So as you can see here on this curve, which I actually had AI generate from a series of different studies, because very few studies have profiled the relationship between knee flexion angle and then all the way across the range of motion. And so I think this is a fair representation. So what you're looking at here, going from left to right on the x-axis, is knee flexion angle ranging from 0 degrees. And so you can see that here the knee is completely extended 0 degrees. And that corresponds with a short MTU unit or short MTU units, right? Multiple muscles, primarily the quadriceps. And then as we move from left to right, we are increasing knee flexion angle. And so we are flexing more and more and more all the way up to 120 degrees. So very deep knee flexion. In that position, with deep knee flexion at 120, of course, the quadriceps are going to be lengthened, and so that's indicated here. So what you're looking at is isometric force production. So fixing the joint at a 0 degree angle, knee straight, and having that individual generate as much force as possible. And you can see in that position where the MTUs are short, relatively short, there's not much force production. There's some, it's not zero, but that as you change the joint angle and fix the joint angle and have the individual generate peak isometric strength or force, you can see that as that angle changes and the MTU length changes, that force producing capabilities go up. This is referred to as the ascending limb of the length-tension relationship because as you increase knee flexion angle, the force capability is ascending. This is referred to as the plateau region, you can see that there is a knee angle that corresponds with peak force production or torque production, and that happens to be around 60 to 80 degrees of knee flexion. And then if you go deeper than that, elongating the MTUs further, you can see that we start to transition into the descending limb of this relationship. And so there comes a point where, again, the MTUs are stretched or elongated so much that your ability to generate force becomes limited. So that gives you an idea of what we're talking about when we are talking about the length-tension relationship or the joint angle torque relationship. So what we're interested in biomechanics is what is responsible for this relationship. So one of the reasons why we observe that joint angle torque relationship across the knee is almost certainly due to the amount of active force production in each of the muscle tendon units. And this is going back to sort of the classic length-tension relationship. And this relationship is one that was observed in isolated animal muscle. It was actually frog muscle that was fixed at different lengths and then stimulated to contract. This was done over 100 years ago by a scientist named Blix. And what he observed was a similar pattern to what you just saw across the knee, where in really short muscle, when you stimulated the frog muscle to contract, it wasn't able to generate as much force as when it was a little bit lengthened. And then when it was stretched quite a bit, then the force generating capacity was actually impaired. And so that observation has been repeated over and over. This is actually one from an isolated muscle fiber from a human muscle biopsy. This was shown in the 60s and plenty of times thereafter. But all that happens here, so this is an aerial view, a bird's eye view of a muscle fiber, and it's connected to a force transducer in these motorized arms, these metal pieces that you see. So this is the muscle fiber that's suspended in solution. And what you can do is you can move this motor arm to stretch out the muscle fiber a little bit so as to study the length-tension relationship. And when you do that, that actually changes the length, of course, of the sarcomeres. And so that is what is believed to contribute to the length-tension relationship seen in an individual fiber or an isolated muscle, is the actin and myosin overlap, which gets at active force production, right? Because that's where the active force is coming from. It's coming from the myosin heads as they attach to the thin filament and pull this thin filament towards the M line. Okay, so all we're looking at here, A and B, is again a a length tension relationship rather, where you see the sarcomere spacing going from short, so that would be a really shortened muscle fiber, and you can see, so number 6, corresponding with 6 here, that there's very little opportunity for myosin to overlap with actin, and therefore you're not going to get much force production. Versus an elongated fiber, so on the other end of the extreme, so number 1 corresponding with number 1 here, you see these myosin heads don't have very many opportunities to grab a hold of this thin filament and pull, right, like a tug of war. Where you see more force production, active force production, is when you have more overlap. So here you can see all of these myosin heads coming off of this thick filament are trying to grab, and they have plenty of opportunity, right? It looks like every single one of them has an opportunity to grab a hold of this thin filament and pull. And so in this position, because of the optimal actin-myosin overlap, number 2, you see some of the highest, see, tension on the y-axis, some of the highest force generation. And so again, the length-tension relationship was first observed in preps like this. It is elegant, but it's oversimplified. No doubt, though, that when we change joint position and change the length of a muscle tendon unit, the position of the sarcomeres and the overlap of the actin and myosin definitely contribute to the ability of the MTU to generate force actively. So that is one reason why we saw the relationship across the knee like we did earlier. Okay, another concept is passive force production at different MTU lengths. And so here's a video, a short video from Muscle in Motion. Right, so we can imagine that we isolate a muscle, we attach it, and then we stretch it. See them stretching the muscle out. Well, the muscle actually has elastic properties because of the connective tissue in muscle, and then the titin protein that's found in muscle is also elastic, so it's sort of like stretching a rubber band. It's going to try to recoil and generate some tension. Of course, in an MTU unit, you're also have the potential to elongate the tendon, and our tendons are very elastic. And so by stretching out muscle and tendon, you get passive force production. And that's going to contribute to the total torque that's generated across a joint. And you can see that added to the classic length-tension relationship is this passive tension that you get when you elongate the MTU. And this is just another sort of cartoon visual of that if you imagine the MTU like your bicep crossing the joint and think about it as a stretched elastic band, the more you stretch or elongate that, so if you increase joint angle here, another factor that we must consider is this concept of moment arms. Now, this is something that will likely be discussed later on in biomechanics lecture. It's really important to our understanding of force production. So when we talk about moment arms, and this isn't, by the way, this is not meant to give you an exhaustive understanding of moment arms, but here's why moment arms matter. It's related to leverage. And so in this example, whether you're grabbing the wrench at 1 foot away from the axis of rotation, which you could imagine is the center of your joint of interest, or you're grabbing it 2 feet away, that is going to influence the total amount of torque that is transmitted around this axis. And so to figure out the torque, what you would do is you would take the amount of force that's being applied, so in this case 20 pounds, and multiply it by the distance from the axis. So here we have 20 pounds of force applied to 1 foot of moment arm, and so we would get a torque of 20 foot-pounds. Generally, we like it to be expressed in Newton meters, but we're going to keep it simple here. Conversely, if you grab the wrench 2 feet away, to generate the same 20 pounds of torque, all you would need is to pull with 10 pounds of force, right? Because you take 10 pounds of force multiplied by 2 feet gives you 20 foot-pounds. So because that moment arm is longer, right, that gives you more force potential. So another way to think about it is if in hand B, if you were generating 20 pounds of torque, just like you were in hand A, then that would double the force or torque production around this axis of rotation, right? Because if this was 20 pounds times 2 feet, that'd be 40 foot-pounds of torque around that axis of rotation. Well, it turns out that moment arms exist in biology, in an intact human. And so this is one way to look at it. So this is taking one muscle across a generic joint, and depending on where its origin is and where its insertion is, it is going to be some distance away from that axis of rotation, the center of the joint. And so generally how we measure this is we start with the center of the axis of rotation, and we draw a line that's perpendicular to where the muscle force is being transmitted. That's called the muscle force line of action, right? So if this muscle is trying to pull and its insertion point here and its origin is here, this is the line of force production or the line of action. And the distance away from the joint then gives us what the moment arm is. So you can imagine if you have a setup, same origin, but the insertions are in different spots, right? We can think about it as an individual muscle. So if a muscle is set up as like what's shown here with position A, again, we could measure the motor arm from the center of the axis of rotation, or the center of the joint, which is the axis of rotation, and draw a line perpendicular to this line of action. And you can see that the moment arm would be, I don't have units here, but it would be this long. Versus if the insertion point was out further, more distal, then that moment arm would be much longer. And so what that means is you would have two muscles, and or a muscle that's positioned in one or two different fashions, if it's generating the same amount of active and passive force, what's being transmitted in torque around this axis is going to be quite different. Position B would have greater torque potential because of that greater lever arm. So it turns out that when you look at like the brachioradialis across the elbow joint, it changes as you change the joint angle through elbow flexion. So this is a few different subjects that are being represented here. But again, getting back to the joint angle torque relationship, the moment arm changes because the muscle to joint distance changes as you rotate a given limb or bone through its range of motion. And so if you fix the elbow flexion angle at 40 degrees, you would have brachioradialis moment arm at 4. If you fixed it at 120 degrees, you would have brachioradialis moment arm at 6. And so that's two completely different torque potentials. And so you can see how that would contribute to total torque production. So it should be clear now that it's not just actin and myosin overlap. It also is the fact that there are changes in moment arm lengths as you move through a given range of motion. Okay, as referenced before, we're almost always dealing with multiple muscles acting across the joint. And so what I want you to realize is that, even though the joint angle might be fixed, the resting length of these different MTUs are going to be different. And you can see that here looking at vastus medialis and vastus lateralis, sarcomere lengths are different at the same joint angle. Right? So at a joint angle of 45, you see longer sarcomere lengths in the VM compared to the VL, and the same is true at 90 degrees. And so what this suggests to us is that there's more active force potential if you're just looking at sarcomere length in the VL than there would be in the VM because of the actin and myosin overlap that we discussed earlier. Not only that, but because the muscles are at different lengths, there's likely different amounts of passive force production. So not only is it different across different MTUs, but it also changes according to the knee joint angle, or joint angle, in this case knee joint angle. This is the final factor that we're going to discuss today. As I mentioned before, the moment arm, and I showed you in the brachioradialis, changes, right? It changes length, the moment arm does, as you move through different joint positions. Not only that, remember, there are almost always multiple MTUs involved, and so this is a comparison of two, brachioradialis compared to the biceps brachii. And you can see, again, in both cases, as you change the elbow angle, it changes the moment arm. Not only that, at a given angle, so let's take elbow flexion angle of 80 degrees, we see a biceps brachii moment arm of around 4 centimeters, whereas the brachioradialis moment arm is around 6 centimeters, indicating that these two muscles and others as well have different torque producing capabilities. All of this is impacting the joint angle torque relationship. So finally, and I apologize, this is a little bit longer than anticipated. This is your take-home message for the fridge. So you can post it on your fridge at home. We looked at this at the very beginning, so the relationship between knee flexion angle and torque production. I want you to understand, hopefully you can appreciate this by now, is that force production is impacted by joint position, but that this is due to not only just actin and myosin overlap, it's due to a net of manifold factors emanating from all of the joint-specific MTUs. This is a team outcome. And this matters. This relationship matters. It matters during rehab. Clinicians may want to avoid training at joint angles where muscles are weakest or joints are vulnerable. It matters for performance, perhaps loading muscles at angles where they're weaker or stronger, depending on the goal of the session. Finally, the last take-home is that the most extreme joint angles typically are suboptimal for torque production. And again, this has implications for injury risk and mechanics. So that's all I have for now. Until next time, science like champions.